Well, Adrian, this appears to be about a 10-year-old oil-burning furnace. This would be perfect for us to do some diagnostic testing. Now, how do you begin the process when you're dealing with an oil burner?
Well, the first thing I always like to do, no matter where I test, or any furnace that I test, is to go upstairs and do a visual walk around first, and to have a small conversation with the homeowner so they feel comfortable with me and I can probably glean some information. I'll be checking supplies and returns, see if the returns are covered like we did with the gases. But there's one difference. I will look specifically at the supplies. And the reason I want to look at the supplies is to see if there's some like soot or residue, or there's a fanning effect over the top that should be darker. And what I will do then is run my finger across the top because I don't want to smear it on the wall. And I run my finger across the top and I'll look at it. If it's oily, then it's potential that there's a cracked heat exchanger, poor misfiring furnace.
Okay, so that sounds like a pretty important differential between inspecting a gas-fired unit and an oil burner. Make sure you pay close attention to those supply registers. And you said right across the top, rub your finger. It's going to smear if it's oil.
That way you're not smearing it across the wall. And then I will check the thermostat. When I check the thermostat, I'm going to record the temperature that I have so I can return it back to the state that I found it so I don't get a phone call down the road.
Sure.
And then I will ask the homeowner a few questions like, when's the last time the unit has been cleaned and tuned? Does the air feel warm when it comes out? Does it bang? Does it pop? Does it make noise? Because you'll never know that furnace as well as that homeowner will.
Okay, so you complete your conversation and communication with the homeowner. It's time for the visual inspection. How do you begin that?
Well, the first thing I like to do is I like to check the fuel lines, just like we do with all the other systems. With an oil system, we can't check with a tester, so we have to do it visually. So what I like to do is go to the tank, I take a piece of paper towel or a white napkin, and I will check the valve, I'll check the bottom of the canister, I'll check the sides of the canister where the O-ring is, I'll check the union. What I'm looking for when I pull it back is I will have a little bit of reddish or yellow tinge to the paper, and that means that there's a potential for an oil leak. You visually inspect underneath the tank to see if there's any pinholes in the tank that are dripping down that can create a problem. And then I'll chase that system, just like we did with the natural gases and the LPs. I'll chase it all the way from the tank to the termination at the furnace, or if it passes on through, like in this case, I'll check all them too. You're also looking for kinks and bends.
Okay, so is it important to do this inspection with the furnace sitting idle, not running?
Yes, because this pump pulls a negative pressure on the fuel line and pulls the fuel to the furnace. When it's sitting idle is when you have your oil leaks. Otherwise, when it's pulling, natural pressure will portal inside the cracks.
And, you know, from the auditor standpoint, don't be surprised if it's buried in a corner, if it's difficult to get to. It seems to me it's imperative that you do these inspections.
Yes,
don't
you have
blow it
to
off.
look.
Okay, so we do a thorough inspection of the fuel tank, the fuel lines, all the unions. We get to the unit itself. What about an exterior visual inspection?
Well, I do the same visual inspection of the exterior, just like we do for the 70s, the 80s, and the 90s and the gases. I'll walk around, I'll document for rust, I'll look for signs of discoloration in the paint. When I have discoloration in the paint like we did for the 80s and the 90s, that's just possibly a sign of a cracked heat exchanger. And it's more prominent in an oil because of the higher temperatures that inside the flue gases are. They run anywhere from 350 to 550 degrees. So that's hotter air, so it's more likely, if it's cracked, to have discoloration on the paint.
Okay, so do a thorough inspection of the box itself. Pay close attention to any discoloration that might occur there. What about the venting?
Well, when I get to the flue connectors, I start to look for things like this little bit of black soot that's pressured back through. I'll look at the stuff at the top. I see this, I'll pull my finger through it and I'll rub it like this.
Wow, look at all that soot.
Yep, that's just the soot that fell or got woofed out to the back of the top of the pipe. And I'll rub it like that, and if it feels oily, the oilier it feels is the more the unit's misfiring.
Okay, so that, from an auditor standpoint, should really heighten your awareness.
It's telling me that probably going to have this unit cleaned and tuned to begin with. And then I'll also go from here all the way up here. I'll look at the top. And then another thing I'll go is I'll check the barometric control, which is located right here on this side. And this is what controls the overdraft of the fire. I want to check this to make sure that it's moving freely and clearly. There's no restrictions. It moves easily. Okay. If it isn't, I'll document it and have the technician come when he works on the furnace to tune it, to free it up and make sure it's working properly. Another thing I'll do is I'll take my flashlight and I'll look inside of the flue. And what I'm looking for is built up of debris, rust, and soot. And over time, some of these units can really get full. I see them filled up to right about halfway, right about up into here.
That much soot can be found inside there?
Yep. So now what you've done is you've taken what would be a 6-inch flue and reduced it down to a 3-inch, which makes it harder to draft. If that is the case, then we'd have to take this apart and clean it.
So really, you're checking that to make sure there's a clear airflow all the way up there, no obstructions in there, so that it's clear venting to the exterior.
Yes, we want to have this unobstructed because that's how all the combustion gases get out of this house. There's no draft assist. It uses its own temperature difference to make it rise out of the house. Another thing we do is a visual inspection of the chimney itself. This is a single wall interior chimney. So it doesn't have a clean out door. It only has a clean out cap. Well, I'm not going to pull that down right now because I don't have the correct equipment to catch everything in case something comes out of there. Continuing with the visual inspection, an auditor should also start looking inside of the cabinet. What I look for, and what an auditor should be looking for when he does this too, is that he should look for the same thing we did everywhere else, dust and debris across the bottom of this decking, or oil underneath the connection here. That means there might be a small oil leak here.
Maybe a good idea to take a napkin or a paper towel around there?
Yep. Another thing we'll do is we'll check underneath the burner itself here to see if there's anything build up, because if there's oil or something down here, that means that this is improperly pitched.
Sure.
Okay? Another thing we'll look for is, just like we did here, I'll look for the connections in here to see if there's any sooting.
Oh, wow, look at, there is some right there.
Yep. That reconfirms that this unit may be misfiring slightly. Okay? Then I'll take my flashlight and I'll look inside of the burner tube to see how much crud or stuff that's built up in it.
And again, you're documenting all these findings every step of the way.
Yep. We'll take a look at this burner motor. This burner motor, what we're looking for is to see if this is an oilable type or not, if there's air ports that need to be cleaned, if it's in solid. The auditor should make sure that he documents all this, because if this is an oiled one, we want to make sure it gets oiled.
And again, all this documentation is so the auditor can convey their findings to the contractor, and then you can double check it once the job is done when you come back.
When the job is all done, this is what I've asked them to do, then you can look at it and see if it's been accomplished.
So the visual inspection before you get into the diagnostic testing is extremely important.
Yes, a lot of information you gather. If you take what you see visually here, what you heard from the homeowner, put them together, you start to get a little bit of a better picture of what's going on. I visually checked the deck, checked my flue, I looked at my connections, make sure my connections are tight. The next thing I'll do is pull this cover off. And now, this is a little bit different than when we did it on the gas, like on the 90 pluses, on the condensating furnaces. There should be no rust in here. If there is, it should be real light rust from just the moisture content from being in a basement. I'll visually inspect for dust and dirt, just as we did with the other furnaces. I'll reach in and I'll feel the blower cage. The more that's built up, the less air that it moves. So we'll make sure that that gets cleaned. I'll do the same thing with this motor as I did with this one. I'll visually inspect to see if it is an oilable type or it has the sealed bearings. If it's oilable, I'll document that it needs to be oiled.
Sure. So what I'm getting out of this, very important to do the visual both inside and outside before you start the diagnostic testing. And I'm assuming that you always want to have the unit shut off before you start a visual inspection.
Yes, that should be one of the very first things you do, is turn the unit off, because you don't want it to fire while your hands are in anywhere else. You want to have control of that unit so you're working in a safe manner.
Okay, well, before we get into the diagnostic testing, let's step back and talk about the sequence of operation, or really how this oil burning furnace operates.
Okay, well, the sequence of operations on an oil furnace is very similar to the sequence of operations on a 70% gas furnace. The first thing that happens is the thermostat senses that there's a need for heat. It sends a signal down to the primary control. The primary control then tells the burner motor to come up. When it comes up, it also starts to pump fuel. It pumps fuel down through the burner assembly and out through the nozzle. It tells the transformer at the same time to energize. When it energizes, it sends 10,000 volts down through the electrodes, and it jumps between a gap, and that keeps a constant spark, okay, to keep the fuel burning. So now that the burner is up, it heats up the furnace to the desired temperatures that's set on the fan control. The fan control brings the air handler up. When the house has reached the temperature that the thermostat has been set for, what happens is the burner shuts down, and then the air handler removes the rest of the heat, and then it just goes back and sits dormant waiting for the next call. As with the gas furnaces, there's a series of tests that we need to perform on an oil furnace. And they're very similar, except for locations, but we added a couple more tests. One of the first tests I like to perform is spillage test. That way I know I'm being safe and I'm keeping the homeowner safe. So what that entails is I set the temperature at the thermostat, I come down here so I can control it to switch.
Okay, so you turn this off, go up to the thermostat, turn it to a nice high reading so that you could have
Now I have control where I have in close proximity where I want it. Then what I'll do is I'll turn this on, and I'll take my smoke generator, and I'll go back to the draft diverter, and what I'll do is just like we did on the 70s and 80s, I'll pass it up along the barometric control, and I will clock it after 1 minute. I can't have spillage after 1 minute. We're very fortunate with this one because we started getting draft right in a matter of seconds.
Sure, it only took about 6-7 seconds, and it was going up.
Yep. So we know we don't have to worry about spillage here. So the next test I would like to perform is the draft test, and that has to be done at steady state. So it takes a couple more minutes for everything to warm up.
Sure.
Then what I will do is take my manometer and my probe. I'll pick a point between here and the first elbow, probably midway, drill a hole. And I'll take my probe, stick it in, bring it back so I got the center. And the reason I want the center is that's the hottest point, and that's where the true draft is. If the pipe is too small, I can have spillage. If it's too large, then I don't get true draft if I'm measuring in the wrong spot. Okay. So I'll get it centered, then I'll take my reading, and that's all there is to a draft test.
And at each step of the way, the auditor makes sure that he documents his findings all the way through from the spillage test to the draft test.
The spillage test and then the draft test. And then you need to check your manufacturer's manual or your program directive for what the draft should be at a certain period of time. Well, the next test that I like to perform is the over-fire draft test. I like to perform it now because the unit is at steady state, I know my draft is adequate, and I have no spillage. Okay? So what I do with that is I go to the observation port, which is located right in front of the furnace, and I open it up, and I'll take a long probe, slide it in, and I close the lid, connect it to my manometer, and then I just watch it, take a reading.
And that probe is actually going into the burning chamber,
Yes,
right?
It goes into the burning chamber. And the reason we want to measure that over-fire draft is these things pull a massive amount of air in draft. They pull about 10 to 15 pascals.
Wow, that's a lot more than a gas furnace.
Yep, a lot more than gas. So we don't want it to misshapen that flame or cause impingement. Okay? And what ideally we want is 0.02 inches of water column or 5 pascals measured over the fire.
So this seems to me to be a very important test because you want to ensure that that draft is not misshaping that flame. It's keeping it nice and straight and not swaying it one side to the other?
Yes, because once it starts to go to one side or the other, if it strikes the side of the burning chamber or the fire pot, it can start to create soot and other concerns.
And of course, it's probably a good idea to compare your results to the PMI?
It's always a good idea to compare your readings to what the PMI is. And if you don't have a PMI, then you revert to your program directives. Another test an auditor needs to perform is a smoke test. And it's only performed on the oils. It's the only furnace that it is performed on.
Okay, so what does a smoke test provide?
The smoke test provides us with information on how much smoke is being produced in the flue gases.
And then what type of equipment are you using?
We use a pull tester. It's a very simple piece of equipment. We take a piece of special paper, we put it inside here, we take this probe, we stick it into the same hole where we did draft test. We do 10 slow, long pulls.
Okay, without removing that probe, you're just simply, like a bicycle pump almost, just pulling it out.
Just a hair slower.
And that's actually sampling that?
Yep, it's pulling an air sample through here. Then I'll take that paper out and I compare it to a chart. That will tell me what the amount of smoke is in that unit. We're very fortunate with this one. This one has zero smoke, which is clean and white. Okay? Now, if it had a yellow trace to it, that would mean that there's unburnt fuel, and there's a sign of a problem. Not quite enough to make smoke, but it's unburnt fuel. The highest smoke reading we can have is, this would be grayish, light gray, and that's called trace. And this type of unit, for this burner, that is the maximum amount of smoke allowed. And then there's a whole series of numbers that it goes up for different amount of smoke.
Okay, so an auditor's taking these tests, and really they're just comparing the color of the paper to the chart, and then comparing their results to the PMI? Because do different models have different tolerances?
Yes. So some of the older versions will go up to tolerate up to 1 smoke. And we really want to perform this test before we perform an SSE test, because if we get anything over 1 or 2, we have a potential to damage our furnace testers. Another test that the auditor has to know how to perform is the steady state efficiency test. And when we perform that test, what we're trying to measure is the steady state of the unit, the efficiency. It tells me the stack temperature of the unit. It tells me how much CO that the unit is producing. And it tells me the oxygen content of the air that's being burnt.
Okay, so how do we perform the test?
Well, we perform the test very similar to what we did for the 70 and 80% gas furnaces. First thing we got to do is take our furnace tester, and we take it and we calibrate it to the atmosphere where the air is coming from for the burner.
And in this case, it'd be right here in the air inside the basement.
Yes, it will, just like on the 70s and the 80s.
So first, calibrate your piece of equipment, the furnace tester.
So then the next thing we do is we go to the same hole where we took our draft and our smoke. We slide our probe in, go all the way to the back, and then we bring it back so it's dead center. We want to measure that core. That's what we're trying to measure.
That's really the key for the auditors. Make sure you have the probe in the center of the flue.
We want to measure the core, yes. Okay. So then what we do is we wait till the steady state is. What steady state is when the stack temperature stops climbing and stays stable at 1 point.
And sometimes it takes several minutes to get to there.
Especially in an oil. Oil can take a little longer because the metal's heavier, the flues are bigger.
Okay, so once it reached, in this case, it was in the mid-400s.
Yeah, stack temperature is mid-400, leveled right out about that. And then what we did was we took the oxygen reading, documented that. We documented the CO, which is about 1 part to 3 parts per million. Then we measured the efficiency, which was 85.1 or 85.2, bounced a little bit.
And so as an auditor, you're taking all those readings, documenting them, and then comparing those findings to the PMI?
Yes, we do. We compare it to what the unit should be producing. It's like the efficiency reading, and that has to be within a certain bracket for our programs. The stack temperature is a number that is used in that calculation. The oxygen we need to be between about 4% and about 7% or a little higher. Okay, but the big one is the CO. CO we want to be able to measure just like we do all the other appliances. And we're fortunate on this one, it's running about 3 parts per million.
Good news for the homeowners.
Very good news for the homeowners. As with all the other furnaces we tested, all the gas furnaces, we temporize on an oil exactly the same way. Okay? We locate a plane all the way around our upper plenum that we can get 4 holes in. It's not crucial to always have them on that plane, but it's ideal. In this situation, since we have an A coil, we were able to get 2 on this side and 2 on the other side. And on the other side are slightly higher.
Okay, and so that's okay if you have a good explanation for why you're doing it. In the perfect world, they'd be on that same plane.
Yes, and we're always concerned about the A coil. We don't want to damage it. And we put another hole midway between the shoe and the return, right in the middle of the drop, and that gives us our return temperature. After steady state, you take the readings, you add all 4 of them together, divide them by how many holes that you have or how many test points that you have, and then you subtract the return air temperature from there.
Because you're trying to find the difference there.
The difference between the air coming from the house and the air that's coming from the furnace.
In this case, what did we find out?
Well, we found out this one has a temperature rise of approximately 70 degrees, which is a little bit on the high side.
But you're comparing that
to the PMI.
To the PMI.
Which is on the nameplate.
And so from an auditor standpoint, again, you take those readings, you average them out, you subtract it, you get your temperature rise, and then it's up to you to document that, compare it to the PMI, and then make recommendations based on your findings.
And in this case, I would probably recommend that we may need to increase the CFM of the unit. As with all furnaces, we have to test airflow. Okay? And the 2 tests that we use to do that are exactly the same tests we do on a 70, 80, and a 90. We do a static pressure test, and we do a flow meter test.
Okay, let's start with the static pressure test. What's involved with that?
Well, static pressure is We have to locate a point between the air handler and the filter.
Oh, I remember that from the gas furnaces. That's what you wanted, but there wasn't any ductwork there to drill into, and it looks like the same situation here.
Same situation. So we had to go up and talk to the homeowner, get permission to drill the unit. We drilled a hole here, which is between the air handler and the filter. And then we drilled one here, which is a little bit different because we have an A-coil here. And no way did I want to touch that A-coil, so I dropped it down just a little bit below the cabinet.
And that's a key point for the auditor. Keep in mind, make sure you know whether or not there's an A-coil there. If there is one there, make sure you take precautions not to drill anywhere near that. Just get below it.
As we did with the other furnaces, we need to take this static pressure probe. And then what we do is just like we did before. We set up our manometer. We take a reading down here by making sure that our probe is faced in this direction. Then we come up here and go down like this. Because the airflow is coming up, we get it.
Airflow goes right around and up.
Then we take the two and add them together. And according to the PMI of this furnace, cannot be greater than a ½ inch of water column, or 125 pascals.
And again, you said you're using a manometer.
Yep, the measure.
And these are helping you with all the calculations, and it's helping you take the readings.
Yes. So again, we use the manometer, we point, get our probe down into the airflow, add the two together. Cannot be greater than a ½ inch of water column, or 125 pascals. There are some of the more modern furnaces require like a 0.3 inches of water column, but 90% of them say 0.5 inches of water column.
And again, the auditor will document this, compare it to the PMI, and then make recommendations based on those.
Yes. Higher statics in some areas mean that there may be some decisions need to be made on supply and returners. Like if the return is slightly higher, or the supply is slightly higher, you may need to add a supply, or you may need to correct the returns. The final test we take is a flow meter test. It's taken exactly the same way on all furnaces.
Whether it's a 70, 80, 90, or an oil burner.
It's all the same. And the reason we take this flow meter test, it tells us how many cubic feet of air per minute this air handler is moving through the whole system, both return and supply.
So what we're testing is the CFM of this particular unit.
This particular unit to ensure that we have enough air movement in here so it doesn't cause any damage to the unit.
Okay, well, let's walk through that again to refresh our memories.
We have to take and put a hole in our return drop midway point, which we've already got selected because we've used a temperature rise taken there. And we'll take the static pressure probe, we'll stick it in the direction of flow, connect it to our manometer, and do an NSOP test, which means we take a reading of what the static pressure in here is, so we have it in the calculation.
And that's leaving the homeowner's filter in place.
Yes, always done with a clean homeowner's filter. That's what we're doing right now, is we're measuring the resistance between the filter and what the flow plate would be.
Okay, so you take that reading.
Yep. Okay. Once we have that test, what we need to do is to pull the homeowner's filter out and insert our flow plate. When we put the flow plate in, what we want to make sure is these diamonds always face into the airflow. Okay. And then we select the plate, and then we read the reading. Now, some manometers are different. Some of the older manometers, you have to do a correction factor. You have to go to a chart, find a correction factor, because it doesn't have it built in. This model has it built in, so I don't need to do the correction factors.
And so really, from an auditor standpoint, when you're doing this test, you want to, first of all, test it with the homeowner's filter in place.
A clean homeowner's filter.
Clean homeowner's filter in place. Then you take that out, you replace it with a flow plate, and then compare those two results.
And this does it all for us. When we're all done, after we compared the two static pressure readings, one with this plate in and one with the original filter, it'll give us the CFM on this side. Now, we're fortunate this one's running about 900 CFM. And this right now is probably burning about 90,000 BTUs. So we're right at that point where we should be.
So it seems to me that you take these numbers, you use a manometer to get the different readings. Yep. You document those readings, compare it to the PMI, and that'll tell you
if we're within our parameters that we can be. And it also tells us if we need to make some adjustments like on our temperature rise. If our temperature rise is slightly high, we can increase our airflow up a little bit and bring our temperature rise down.
So it's a good case in point of how all these tests work together to really give the homeowner the best possible system, because you're documenting all the results, you're making recommendations to the contractor can read these, come in, perform all the different adjustments, And at the end, the homeowner's going to have the most efficient operating system possible.
The system will be at its highest SSE. The system will have the proper airflow. It'll have the proper static pressures. So everything works as one unit, and it allows us to tie it all together. All this testing is just so we get the homeowner the most optimum performance out of this heating system that we can.
Depending on your agency's protocols for oil furnace testing, an additional procedure involving the removal of the oil burner assembly and inspection of the oil nozzles should be considered. A common problem found with oil furnace burners is the wrong size or type of spray nozzle that is installed in the oil burner, which can lead to misfiring, inefficiency, and premature wear of the system. The following steps provide an overview for removing the oil burner assembly, conducting a general visual inspection, and checking the oil nozzles to make sure they meet the manufacturer's specifications based upon the heat loss calculations for the home. Step 1 of the process involves a visual review of the transformer and should be done after evaluating the oil burner's initial operation and testing. Remove the transformer cover and start by inspecting the CAD cell for soot or a slight haze which can cause the burner to misfire. Also, visually inspect the springs to make sure they are in good condition and the blower wheel area for excess soot. The next step is to disconnect the oil line and remove the burner assembly. The burner consists of a nozzle, a burner assembly, and an electrode on one side of the nozzle and an electrode on the other side of the nozzle. The nozzle should be cleaned well enough with a cloth or paper towel so the nozzle size can be revealed and documented. With a slight turn of the burner assembly, the nozzle will also display the spray pattern measurement, which should also be documented. Upon recording the size and spray pattern stamped on the nozzle, it should then be checked with the manufacturer's specifications on the furnace to match the BTU needs of the home. Improper nozzle sizing can once again lead to overfiring, inefficiency, and premature wear on the system. Proper nozzle sizing can optimize safety, comfort, and efficiency. Additional procedures for burner assembly include the measuring of the electrodes in relation to the oil nozzle. And for more experienced technicians, adjustments can be made by loosening the electrodes and resetting them with the proper measuring device. Upon completing the inspection and documenting the nozzle sizing and spray pattern, the burner should be reinstalled along with the transformer cover, and all the mounting screws should be re-secured.